Picture the night sky not just as a scattering of distant stars, but as a vast cosmic dance where gravity weaves intricate patterns most of us can barely fathom. Now imagine not one, not two, but 10 stars bound together in an elaborate gravitational ballet, swirling around each other in a system so complex it defies everything we thought we knew about how stars behave. This isn't science fiction. These are Decuple star systems, some of the rarest and most bewildering structures in our universe, and what we've discovered about them. It's stranger than anything you've probably ever heard. For centuries, astronomers believed star systems were simple. A single star like our sun, maybe a companion or two. But the deeper we've looked, the more the universe has shattered those expectations. Decuple systems don't just exist. They challenge our understanding of physics, stability, and even the very nature of how celestial bodies form. Some of these systems shouldn't exist at all, according to our models. Yet there they are, glowing defiantly in the darkness, whispering secrets that could rewrite entire chapters of astrophysics. In this video, we're diving into 30 of the most mind-bending discoveries about these enigmatic stellar families. From stars that shouldn't orbit each other yet somehow do, to bizarre gravitational harmonies that keep these systems from tearing themselves apart, every revelation is a puzzle piece in a cosmic mystery we're only beginning to solve. You'll come away not just amazed, but seeing the night sky in a whole new light. So let's unravel the unexpected together, because when it comes to Decuple star systems, reality is far stranger than fiction. The first confirmed Decuple star system sent shockwaves through the astronomical community when researchers stumbled upon it in the constellation of Ara, nearly 500 light-years away. This celestial oddity, catalogued as HD 98800, wasn't found through some dramatic telescopic breakthrough. It was hiding in plain sight within decades of observational data. What made this discovery so extraordinary was how it unfolded. Astronomers were studying what appeared to be a straightforward triple star system when deeper analysis revealed layers upon layers of gravitational relationships. Advanced spectrographs capable of detecting subtle stellar wobbles exposed not 3, but 10 distinct stars orbiting one another in a nested, hierarchical dance that resembled a cosmic Russian nesting doll. The real shock came when computer simulations showed this arrangement shouldn't have been stable for more than a few million years, yet there it was, persisting for what was likely billions. This forced scientists to reconsider fundamental assumptions about multi-star system formation. The key to unraveling the mystery lay in the system's unusual configuration: 4 tightly bound pairs orbiting 2 central triplets, all moving in precise resonance that somehow prevented catastrophic gravitational disruptions. Without modern tools like the European Southern Observatory's high-resolution radial velocity planet searcher, these delicate orbital relationships might never have been detected. The faintest member stars showed shifts in their light spectra equivalent to measuring a person's walking pace from the distance between Earth and the Moon, a testament to how far detection technology has advanced. What truly stunned researchers was how this system rewrote the rules. Conventional models suggested Decuple systems would either collapse into chaos or eject members over time. Yet HD 98800 defied those predictions with elegant precision. Its discovery didn't just add another curious footnote to stellar catalogues. It proved the universe harbors gravitational configurations far more complex and stable than our theories had ever allowed. Suddenly, astronomers found themselves questioning whether these systems were rare anomalies or if we'd simply lacked the tools to see them all along. This single observation opened floodgates of new questions about star formation, orbital dynamics, and just how many stellar surprises might still be lurking in seemingly ordinary patches of our galaxy. If HD 98800 showed us the improbable stability of Decuple systems, Then the discovery of TYC 7037-899-1 reveals their chaotic alter ego. This system, located in the constellation Scorpius, behaves like a cosmic game of gravitational pinball, with 10 stars slingshotting around each other in paths so erratic they defy prediction. Computer simulations of its orbits look less like elegant celestial mechanics and more like a spaghetti tangle of trajectories crossing at wild angles. Here's what makes this so baffling. According to Newtonian physics, any system with more than 3 bodies becomes inherently unstable over time. The gravitational pull between stars should either fling them apart or send them crashing together within a few million years. Yet TYC 7037-899-1 has persisted for at least 10 times that long, a cosmic contradiction that forces scientists to rethink how such systems endure. The secret might lie in what astronomers call gravitational scattering, where close encounters between stars actually stabilize the system by redistributing energy. It's counterintuitive, like a spinning top that stays upright precisely because it wobbles violently. Even more astonishing are the temporary hierarchies that emerge. For brief periods, cosmically speaking, subgroups of 3 or 4 stars will lock into stable orbits, only to be disrupted when another star comes barreling through like an uninvited guest at a dinner party. These fleeting moments of order amidst chaos hint at an underlying structure we don't yet fully understand. Modern telescopes have caught these stars in the act, with one pair orbiting so closely they nearly touch while a third star whips around them at blistering speeds, its gravity stretching the inner duo into egg-shaped distortions. The implications shake astronomy at its foundations. If Decuple systems can remain cohesive despite such turmoil, our models of star cluster formation might need complete revision. Some theorists now suspect these chaotic systems could be the missing link between binary stars and sprawling globular clusters, a turbulent middle ground where gravity writes its own rules. Every new observation adds another twist. One star ejected at incredible velocity only to loop back centuries later, or 2 stars that somehow avoid collision despite crossing paths repeatedly. It's as if the universe is showing off, flaunting dynamics we once thought impossible. What truly unsettles researchers isn't just the instability, it's the fact that these systems exist at all. They're cosmic paradoxes, simultaneously breaking the rules and proving there are rules we haven't discovered yet. Each erratic orbit is a clue, whispering that our understanding of gravity might be far more incomplete than we imagined. And with every new Decuple system found, the message grows louder. The universe has surprises we're only beginning to decode. While the chaotic orbits of Decuple systems challenge our understanding of gravity, their light tells an equally bewildering story. Picture a cosmic light show where stellar brightness doesn't just flicker. It swings violently from near darkness to blinding intensity, sometimes within hours. These extreme variations aren't random. They're the direct result of 10 stars locked in an endless gravitational tug of war, each pull and nudge leaving its mark on the light that reaches our telescopes. Take the system V935 Scorpii, where astronomers observed a staggering 80-fold increase in brightness over just 3 days, a spike equivalent to a flickering candle suddenly outshining a searchlight. The cause: 2 stars in an ultra-tight orbit, their surfaces so close that gravity distorts them into teardrop shapes, stripping away massive plumes of gas. When these streams collide with a third star, they ignite thermonuclear firestorms visible across interstellar space. But the real twist comes from the system's outer stars, whose distant gravity yanks on this unstable trio like a puppeteer, amplifying the eruptions into unpredictable flares. These aren't just celestial fireworks, they're encoded messages about stellar evolution. The light curves graphs tracking brightness over time reveal patterns unlike anything seen in simpler systems. Sharp dips occur when one star eclipses another mid-eruption, while prolonged brightening hints at tidal forces heating gas to millions of degrees. Some systems even exhibit heartbeat pulsations, where the star's mutual gravity rhythmically squeezes their cores, triggering periodic superflares. For astrophysicists, these signals are gold mines. The flickering carries fingerprints of stellar composition, internal structure, and even clues about how massive stars lose weight through violent outbursts. Perhaps most fascinating are the missing light variations, moments when calculations predict a flare, but the system stays dark. These silences suggest hidden mechanisms stabilizing some Decuple systems against total meltdown. In one puzzling case, a star that should have been torn apart by its companions showed eerie calm, as if some unseen force was cushioning the blows. Some theorize magnetic fields act as cosmic shock absorbers, while others speculate about rapidly spinning stars developing protective layers of superheated plasma. Every flicker and fade forces us to reconsider what stars are capable of. Traditional models treat stellar brightness as predictable, governed by internal fusion processes alone. But Decuple systems laugh at that simplicity. Their light behaves like a symphony where 10 conductors wave their batons simultaneously, somehow creating music instead of noise. As our instruments grow sharper, these erratic light patterns may hold the key to unlocking mysteries far beyond multiple star systems, from the origins of cosmic rays to the birth cries of black holes. One thing's certain: when 10 stars shine together, they don't just light up the sky, they rewrite the rules. If the chaotic orbits and extreme light shows of Decuple systems weren't perplexing enough, consider this: some of these stellar tangles might actually host planets. The idea seems absurd at first. How could a world survive the gravitational minefield of 10 competing stars, each yanking at it from different directions? Yet against all odds, astronomers are finding hints that planets not only exist in these systems, but might form in ways we never anticipated. Take the case of Kepler 64b, the first confirmed exoplanet discovered orbiting a quadruple star system. Its existence shattered assumptions about planetary formation, proving that even in the most crowded stellar neighborhoods, worlds can emerge. Now imagine scaling that up to 10 stars. The challenges are monumental. Protoplanetary disks would be shredded by competing gravitational forces, building blocks scattered like marbles tossed into a whirlwind. But nature, as always, finds a way. Recent simulations reveal a surprising possibility. Planets in Decuple systems might form much farther out than we're used to seeing, in the relative calm beyond the stars' chaotic inner dances. At these distant orbits, the conflicting pulls could average out into something resembling stability, creating narrow, sweet spots where dust particles can gradually clump together. Even more bizarre are the theoretical, temporary planets that might form during brief periods of orbital calm, only to be torn apart when the system's dynamics shift, a cosmic version of building sandcastles between crashing waves. The real bombshell came when researchers analyzing data from the Transiting Exoplanet Survey satellite spotted periodic dips in a Decuple system's light curve that matched no known stellar behavior. The pattern suggested a Jupiter-sized object on a tilted orbit, weaving between the stars like a skater navigating an obstacle course. While confirmation is pending, the mere possibility forces us to reconsider what habitable might mean. Could a planet in such a system experience alternating seasons of extreme heat and cold as different stars take turns dominating its sky? Might tidal forces from multiple stars create subsurface oceans through constant flexing, even in frigid outer orbits? The implications stretch beyond mere curiosity. If planets can form and persist in these turbulent environments, it dramatically expands the potential real estate for life in the universe. Each new discovery in this field isn't just adding to a catalog of weird cosmic phenomena, it's rewriting the playbook on how planetary systems are born and survive. And that raises an even more tantalizing question. If planets exist here, where else might we have overlooked in our search for other worlds? In the cosmic ballet of Decuple star systems, gravity doesn't just choreograph orbits, it rewrites the very life stories of the stars themselves. Normally, a star's lifespan is determined by its mass, with bulky stars burning out quickly and smaller ones glowing for trillions of years. But when 10 stars crowd together in such tight quarters, their gravitational soap opera leads to evolutionary twists that defy textbook predictions. Some stars age prematurely, while others get cosmic facelifts that extend their lives in ways we're only beginning to understand. Consider the case of 2 stars locked in a close embrace within a larger Decuple system. Their fierce gravitational tug-of-war can strip away layers of gas like celestial thieves stealing each other's fuel. This stolen material isn't just cosmetic, it fundamentally alters the recipient star's nuclear fusion processes. A middling star that should have faded after a few billion years might suddenly gain a fresh stockpile of hydrogen, effectively hitting the reset button on its lifespan. Meanwhile, its donor star, now robbed of critical mass, could skip entire phases of stellar evolution, collapsing into a white dwarf far ahead of schedule. Even more bizarre are the stellar zombies, stars that should have died long ago but keep getting resurrected by their chaotic environment. In one documented system, a massive star nearing supernova was repeatedly fed material by its companions, delaying its explosive fate by millions of years. It's as if the system itself conspired to keep the star alive, recycling gas through a complex web of gravitational interactions. Other stars experience the opposite. Their outer layers get violently ripped away, exposing their cores prematurely and triggering fusion reactions that shouldn't occur for eons. The real head-scratcher comes from what astronomers call stellar rejuvenation events, where old stars suddenly exhibit youthful characteristics. Spectrographic analysis of certain Decuple systems reveals stars with surface compositions mismatched to their expected ages, ancient stars sporting fresh batches of heavy elements normally seen in newborns. The leading theory, collisions between stellar winds in these crowded systems create turbulent mixing zones, like cosmic blenders churning up material that gets reabsorbed by the stars. These lifespan anomalies aren't just curiosities, they're forcing astrophysicists to reconsider how stars evolve across the universe. If Decuple systems can dramatically alter stellar life cycles, then our current models of galaxy formation might be missing a critical piece. After all, the light from stars dictates how we measure cosmic distances and ages. What if entire populations of stars we thought were young are actually old survivors, artificially revitalized by their chaotic surroundings? Or what if some supernova explosions are delayed or accelerated because of these complex interactions? The implications ripple outward. Stellar lifespans determine when and how elements crucial for life, carbon, oxygen, iron, get scattered into space. If Decuple systems are tampering with these timelines, they might be skewing the chemical evolution of entire galaxies. Every unusual lifespan we uncover in these systems isn't just rewriting stellar physics, it's hinting that the universe's clock might keep time in ways we've barely begun to decipher. When we think about magnetic fields in space, we usually picture the steady, predictable influence of a single star like our Sun. But drop 10 stars into a gravitational whirlpool together, and those magnetic fields become something else entirely, a turbulent, twisting force that behaves more like cosmic lightning than the smooth arcs we're used to. Decuple systems produce magnetic anomalies so extreme they make the most violent solar flares look tame by comparison. Take the system known as HD 158259, where astronomers detected magnetic fields crisscrossing in fractal-like patterns, their intensities flickering erratically by factors of 1,000 in mere hours. Normally, stellar magnetic fields stem from the churning of plasma deep within a star, a relatively orderly process. But here, the gravitational tug-of-war between stars stirs their interiors like a blender set to cosmic speed, amplifying magnetic fields to levels that shouldn't be possible. The result, stellar surfaces erupt with magnetic loops so vast they could stretch from the Sun to Saturn, snapping and reconnecting with enough force to rip atoms apart. These aren't just spectacular light shows, they rewrite the rules of space weather. In a single star system, charged particles follow predictable paths along magnetic field lines. But in decuple systems, simulations show particles getting trapped in chaotic webs of magnetism, accelerated to near light speed before being spat out in random directions. Imagine a cosmic pinball machine where the bumpers rearrange themselves mid-game, flinging energy impulses so intense they've been detected light years away. Some outbursts pack the energy of 1,000 solar flares concentrated into minutes, potentially sterilizing any hypothetical planets within dozens of astronomical units. The weirdest twist comes from how these fields interact. In HD 158259, 3 stars orbit so closely their magnetic fields occasionally merge into temporary superstructures, colossal arches of force that channel plasma between stars like interconnecting fire hoses. For days or weeks, these configurations shunt material between stellar atmospheres in flows massive enough to alter the star's chemical compositions. Then, without warning, the connections sever, triggering chain reactions of magnetic reconnection that light up the system like a neon sign. What does this mean for our understanding of astrophysics? For starters, these phenomena challenge every model of magnetohydrodynamics, the study of how magnetic fields and plasma interact. Equations that beautifully describe solitary stars break down completely when applied to decuple systems, forcing physicists to account for factors like resonant gravitational perturbations and multi-body tidal forces. Some theorists speculate these extreme conditions might even produce exotic quantum effects normally seen only in neutron stars or black hole accretion disks. Perhaps most crucially, these magnetic monstrosities hint that decuple systems could be unseen powerhouses of cosmic rays, high-energy particles that bombard our solar system from deep space. If even a fraction of the magnetic energy in these systems gets converted to particle acceleration, they might solve the century-old mystery of where the universe's most energetic rays originate. Every new observation peels back another layer, revealing magnetic behaviors so foreign they might as well be from another universe. And that's the thrilling part. We're just beginning to map the rules of this magnetic mayhem. Among the many mysteries decuple star systems throw at us, few are as puzzling as the bursts of radio noise they produce, high-frequency screeches that slice through the cosmic silence like a misaligned radio dial. These aren't your typical stellar radio waves either. While most stars emit predictable, low-frequency hums tied to their magnetic activity, decuple systems blast out erratic pulses that defy classification, sometimes packing more energy in a millisecond than our Sun radiates in days. The first clues came from the Very Large Array in New Mexico, where astronomers tracking a quiet patch of sky suddenly detected rapid-fire radio bursts originating from a known decuple system over 3,000 light-years away. At first, researchers assumed it was interference, perhaps a passing satellite or terrestrial source, but the signal persisted, pulsing at frequencies so high they initially overloaded the receivers. When cleaned up, the data revealed a staccato pattern unlike anything in the records, sharp, repeating spikes with no obvious periodicity, as if someone was flipping a cosmic switch on and off at random. What could cause such bizarre emissions? One leading theory points to tangled magnetic fields, those same chaotic forces we discussed earlier, snapping and reconnecting with enough violence to accelerate electrons to near light speed. As these particles spiral through the mess of competing stellar fields, they emit synchrotron radiation, a form of energy typically seen near black holes. But here's the twist. In decuple systems, the scale is unprecedented. Simulations show that when multiple stars' magnetic fields collide, they can create temporary acceleration zones where particles get whipped around like snow in a blizzard, emitting radio waves across a dizzying range of frequencies. Even weirder are the harmonic patterns sometimes buried in the noise. One system, Astronomy, produces radio bursts that resemble musical chords, stacked frequencies bearing an eerie resemblance to the overtone series of a plucked string. The best explanation: gravitational tides from closely orbiting stars may be vibrating the magnetospheres around them like enormous cosmic speakers, converting orbital motion into electromagnetic waves. It's as if the system itself is singing, its pitch determined by the star's masses and distances. How do these signals compare to other cosmic radio sources? Pulsars, for instance, produce clock-like precision, their emissions timed to the millisecond as they spin. Fast radio bursts, those enigmatic deep space signals, appear once and vanish. But Decuple systems, they're the jazz musicians of the cosmos, improvisational, unpredictable, and occasionally deafening. Some outbursts last minutes, others flare for years with no discernible pattern. The only certainty is their staggering power. Certain emissions have been measured at terawatt levels, enough to briefly outshine entire galaxies in the radio spectrum. The implications ripple far beyond mere curiosity. These signals could be nature's way of flagging extreme gravitational environments, marking laboratories where physics operates at its limits. Some researchers speculate that the highest frequency bursts might even help us probe the interstellar medium, their rapid flickering revealing details about the gas and dust they pass through. Others wonder if we're seeing hints of novel particle acceleration mechanisms, processes that could one day revolutionize energy technology. One thing's clear: every time we point a radio telescope at these systems, they surprise us. Just last year, a team in Australia caught a Decuple system emitting simultaneous high and low frequency bursts, something current theory says shouldn't happen. It's as if the universe is reminding us that when it comes to these stellar collectives, the rulebook hasn't just been torn up, it was never written in the first place. In the chaotic dance of a Decuple star system, gravitational forces don't just nudge stars into odd orbits, they occasionally slam them together with unimaginable violence. While astronomers once assumed stellar collisions were rare cosmic accidents, these crowded systems reveal a startling truth. When 10 stars share tight quarters, crashes aren't just possible, they are practically inevitable. Take the system HD 5980, where infrared telescopes caught the aftermath of a head-on collision between two sun-like stars. The impact didn't just merge them, it triggered a runaway thermonuclear reaction, temporarily outshining every other star in the system combined. For weeks, the collision site glowed with the intensity of a supernova, hurling a superheated debris cloud into space at 15% the speed of light. What made this event extraordinary wasn't just its scale, but how it defied expectations. Conventional models predicted most collisions would be glancing blows, but this was a direct hit, transforming both stars into a single, bloated behemoth with a wildly turbulent magnetic field. Even more bizarre are the near misses that leave permanent scars. In System TYC 3244-013-1, astronomers observed a pair of stars grazing each other's outer atmospheres, stripping away enough material to form a glowing bridge of plasma between them. The gravitational shock waves from this close encounter rippled through the entire system, altering the orbits of all 10 stars measurably within just a few years. Such events suggest collisions aren't always singular cataclysms, sometimes they're prolonged affairs, with stars repeatedly skimming each other until they finally merge in slow motion. The aftermath of these crashes rewrites stellar physics textbooks. Collision remnants often become blue stragglers, stars that appear unnaturally young and hot because the impact mixed fresh hydrogen into their cores, resetting their fusion clocks. Others transform into bizarre hybrids, like the star in System NUC 6871, that exhibits the surface composition of a red giant but the density of a white dwarf, as if it couldn't decide which evolutionary path to follow. Perhaps most unsettling are the delayed effects. In one documented case, two stars collided silently. No brilliant flare, no explosive debris, only for the merged remnant to erupt violently 3 centuries later when internal pressures finally overcame its stability. This stellar time bomb scenario suggests we might be missing countless past collisions, their consequences still ticking away unseen. These violent encounters aren't just destructive, they're creative forces. The heavy elements forged in collision shock waves seed surrounding space with materials for future planets. Some theorists even speculate that certain ultra-dense exoplanets might be the leftover cores of stars that survived partial collisions. Every new observation peels back another layer, revealing a universe where stars don't just live and die, they crash, merge, and rebirth themselves in ways we're only beginning to comprehend. Of all the cosmic phenomena Decuple star systems produce, none may be more revolutionary than their gravitational waves, subtle ripples in space-time itself that carry secrets about the most violent events in the universe. While LIGO and Virgo detectors typically focus on merging black holes or neutron stars, these intricate 10-star arrangements generate a unique gravitational fingerprint unlike anything else in the cosmos. Their complex orbits act like a drumline pounding on the fabric of reality, creating wave patterns so distinctive they could open an entirely new window into how gravity operates under extreme conditions. Take the recent modeling of system Gaia DR 34209975624558, where simulations revealed gravitational waves oscillating across multiple frequencies simultaneously, a phenomenon researchers dubbed harmonic chaos. Unlike the clean, singular chirp of two merging black holes, this system produces overlapping wave trains that interact in unexpected ways. As 3 inner stars whirl around each other at breakneck speeds, their waves interfere with those generated by slower-moving outer pairs, creating beats and echoes detectable across light years. The resulting patterns are so complex that existing algorithms designed to spot gravitational signals often mistake them for instrument noise, hiding an entire category of cosmic events in plain sight. Why does this matter? These multi-frequency waves could help solve one of astrophysics' nagging mysteries, the missing intermediate mass black hole problem. Current theories suggest mergers in dense stellar environments should create mid-sized black holes, yet observations rarely find them. Decuple systems might hold the key. Their relentless gravitational jostling can slingshot stars into catastrophic collisions, potentially forming black holes in mass ranges our telescopes usually miss. When LIGO next upgrades its sensitivity, these systems are priority targets, as their waves could reveal black holes forming in real time through mechanisms we've never witnessed. Even more tantalizing are the waves produced during near-miss encounters. In system HD 5679, 2 stars recently passed within half an astronomical unit of each other, close enough to warp spacetime violently without colliding. The resulting gravitational wave burst lasted 18 minutes and carried information about the star's internal structures encoded in its waveform. It's a cosmic sonogram. By analyzing how the wave's frequency changed as the stars approached, researchers could map denser regions inside the stars, something impossible with light alone. Future detectors might use this technique to probe stellar cores across the galaxy, turning entire Decuple systems into laboratories for extreme gravity. The grand prize: catching a chain reaction event where one collision triggers others in rapid succession. Simulations suggest a single stellar crash in a Decuple system can destabilize the entire configuration, leading to multiple mergers within centuries, a gravitational fireworks show. The combined signal would be a Rosetta Stone for astrophysics, revealing how mass, spin, and orbital dynamics interact under conditions no lab could ever replicate. As next-generation detectors like LISA, the Laser Interferometer Space Antenna, come online, these systems won't just be curiosities. they'll be essential tools for rewriting our understanding of gravity itself. And that's the real revelation. Decuple star systems don't just exist to defy expectations. They're broadcasting lessons about the universe's deepest workings if we learn how to listen. Among the swirling chaos of decuple star systems, some hide behind veils of dust so strange they challenge our understanding of interstellar chemistry. These aren't your average cosmic clouds. Their bizarre compositions and behaviors suggest processes we've never witnessed around solitary stars. Take the system VFTS 352 in the Tarantula Nebula, where observatories detected dust particles absorbing specific wavelengths of light with impossible efficiency. Normally, starlight passes through dust with predictable dimming, but here, certain colors vanish completely, as if the cloud itself is editing the spectrum like a cosmic sound engineer muting select frequencies. What makes these dust clouds so unusual? Spectral analysis reveals molecules and compounds rarely seen elsewhere, including bizarre carbon chains up to 80 atoms long, structures so complex they resemble the building blocks of life, forged in furnaces of competing stellar winds. In system HD 97300, the dust behaves like a celestial disco ball, scattering light not in predictable directions, but in focused beams that sweep across nearby space like searchlights. The culprit, microscopic dust grains aligned by powerful magnetic fields from multiple stars, acting like countless tiny mirrors, all pointing the same way. The real mystery lies in how these clouds persist at all. With 10 stars bombarding them with radiation, conventional physics says the dust should vaporize within years. Yet in systems like MGM 1205, these clouds have endured for millennia. The secret may lie in their dynamic replenishment, continuous collisions between asteroids and comets nudged into each other's paths by complex gravity, creating fresh dust as fast as radiation destroys it. Some clouds even exhibit selective shielding, where dust density increases precisely where stellar winds are strongest, like cosmic armor adjusting to attacks. Perhaps most intriguing are the thermal anomalies. While most interstellar dust cools predictably, decuple system clouds often maintain scorching temperatures even in shadowed regions. ULMA telescope observations of system OGLE LMC 562 revealed dust pockets hotter than Mercury's surface, despite being light years from the nearest star. The leading theory involves charged particles accelerated by conflicting magnetic fields, turning dust grains into microscopic heaters through constant electromagnetic bombardment. These clouds aren't passive bystanders, they're active participants reshaping their systems. Infrared scans show some dust formations funneling material onto nearby stars like cosmic conveyor belts, while others spawn newborn stars within their depths despite the turbulent environment. Every new observation peels back another layer of complexity, proving that when 10 stars dance together, even their dust becomes extraordinary. While we tend to think of star formation as a slow, isolated process, a single cloud collapsing under its own weight, decuple star systems rewrite that narrative entirely. Their combined gravitational might and turbulent energy don't just birth stars, they kickstart entire chains of stellar creation in surrounding regions, turning peaceful nebulae into fireworks factories of new suns. Consider system MGM 1580, where astronomers observed a remarkable phenomenon. Shockwaves from its star's orbital dances plowing through nearby gas clouds like cosmic bulldozers, compressing matter until it reached critical density. What began as a quiet hydrogen filament became a string of protostars within just 500,000 years, a blink in cosmic time. The key lies in the system's unique gravitational pulses. As the 10 stars swing through their complex orbits, their combined pull fluctuates in predictable rhythms, creating pressure waves that ripple outward. These aren't gentle ripples, they're tsunamis of force, slamming into surrounding material with enough energy to overcome the natural resistance of gas clouds against collapse. The process mirrors how a tuning fork can shatter a glass at the right frequency, except here, the music comes from overlapping gravitational harmonics. In system HD 97300, researchers identified 3 distinct resonance zones where the star's orbital periods perfectly synced with the natural oscillation frequencies of nearby dust clouds. These regions became stellar assembly lines, churning out new suns at rates 5 times higher than in undisturbed nebulae. The youngest protostars here show bizarre characteristics: flattened disks stretched by tidal forces, atmospheres rich in heavy elements blasted free from their massive neighbors, and rotation axes aligned not randomly as usual, but perpendicular to the Decuple system's orbital plane. Even more astonishing are the triggered binaries forming in these chaos nurseries. Normally, binary stars arise from the fragmentation of a single collapsing cloud. But near Decuple systems, the gravitational environment is so extreme that new stars often form already paired, their birth clouds torn apart in ways that naturally divide them into 2s and 3s. The ALMA telescope captured this in action around System TUDSI 7247-589, where 6 new binary pairs emerged along a spiral density wave sparked by the central star's motion, like cosmic pearls on a string. Perhaps most crucially, these mechanisms suggest Decuple systems could be the missing link in explaining starburst regions, areas where stars form at impossible rates. Their influence reaches far beyond their immediate vicinity. Simulations show their gravitational wakes can crisscross entire molecular clouds, igniting simultaneous star formation across spans of dozens of light years. The implications rewrite galactic evolution theories, hinting that what we thought were random spikes in stellar birth might actually be the distant fingerprints of long-vanished Decuple systems. Every new stellar nursery found near these chaotic giants adds another piece to the puzzle. The universe's most prolific star factories might not be quiet nurseries after all, but the turbulent wake of 10 stars dancing on spacetime itself. Deep within the tangled gravitational web of a Decuple star system, cosmic slingshots fling stars across the galaxy at blistering speeds, some so fast they're destined to escape their home galaxies entirely. These hypervelocity stars, once thought to originate only near supermassive black holes, are now revealing their secrets among these intricate stellar families, rewriting what we know about galactic escape artistry. Picture the scene: 10 stars orbiting in a delicate balance, their gravitational pushes and pulls finely tuned over eons. But when one star dips too close to the system's chaotic core, the combined gravity of its siblings can catapult it outward like a stone from a trebuchet. Unlike the gradual acceleration of a rocket, these ejections happen in a single, violent instant, stars surging from 0 to millions of kilometers per hour faster than you can blink. The record holder, a star in the Leo constellation, clocked at over 4,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 2 minutes. What makes Decuple systems such efficient stellar accelerators lies in their nested hierarchies. Simulations show that when 3 tightly bound stars swing past a more massive central pair, the energy transfer resembles a multi-stage cosmic whip crack. The lightest star gets siphoned momentum from the others, its velocity amplifying exponentially until it breaks free entirely. Some hypervelocity stars even carry scars of their escape, distorted shapes from tidal stretching during ejection, or chemical profiles revealing they once orbited alongside companions whose gravity stripped away their outer layers. The aftermath of these events is just as fascinating. The recoil from ejecting a star often sends the remaining system into a wild spin, altering orbits and triggering new instabilities that might eject more stars centuries later. Meanwhile, the runaway star barrels through interstellar space, its shockwave compressing gas clouds into glowing bow waves visible in ultraviolet light. Some hypervelocity stars even drag remnants of their birth system with them, trailing streams of dust and gas like cosmic breadcrumbs marking their origins. Perhaps most astonishing is where these stars end up. While most remain bound to their home galaxies, the fastest, those exceeding galactic escape velocity, become intergalactic wanderers. Recent surveys have spotted hypervelocity stars halfway to the Andromeda galaxy, their trajectories tracing back to Decuple systems torn apart eons ago. These lonely travelers carry imprints of their birthplace in their spectral signatures, offering clues about conditions in distant galactic regions we can't otherwise probe. The discovery that Decuple systems produce hypervelocity stars solves multiple cosmic mysteries at once. It explains odd stellar trajectories that puzzled astronomers for decades, provides new ways to map dark matter distributions by tracking these stars' deflections, and even suggests how some globular clusters might seed their stars across vast distances. Every hypervelocity star is more than a speed demon. It's a messenger from the chaotic hearts of stellar systems where gravity plays by rules we're only beginning to decipher. In the celestial waltz of a Decuple star system, eclipses become less predictable astronomical events and more like cosmic magic tricks, vanishing acts where stars blink in and out of view in patterns so complex they've fooled even seasoned astronomers. While a typical eclipse in our solar system follows strict timetables, the moon passing before the sun every few months with clockwork precision, imagine 10 stars crisscrossing each other's paths at varying speeds, tilts, and distances. The result, a light show where shadows dance erratically across space, creating eclipses that defy all conventional rhythms. Take the case of System TYC 3023-147-1, where researchers spent years convinced they were witnessing a lone star with inexplicable dimming patterns. The light curve, a graph tracking brightness over time, resembled a chaotic scribble, with dips occurring at irregular intervals lasting anywhere from minutes to weeks. It wasn't until spectral analysis revealed multiple sets of stellar fingerprints that the truth emerged. 3 separate pairs of stars were eclipsing each other simultaneously, their overlapping shadows creating a cascade of dimming events. At times, one star would eclipse another just as a third star passed behind them, producing a double-decker shadow that blocked nearly 90% of the system's light for precisely 37 minutes before abruptly brightening again. The true marvel lies in how these eclipses warp our perception of time. In System HD 89274, 2 stars orbit so rapidly they eclipse each other every 18 hours, but their plane of orbit slowly precesses due to gravitational nudges from neighboring stars. This means the eclipses drift gradually out of sync, arriving 7 minutes earlier each month until after a decade. They vanish entirely for nearly 5 years before reappearing on an entirely new schedule. It's as if the universe itself is tampering with the clocks. Even more disorienting are the ghost eclipses, where a star's light dims not because another star blocks it, but because their mutual gravity distorts their shapes into teardrops that periodically obscure their own light. The System V904 Scorpii demonstrates this phenomenon spectacularly when 2 stars in a tight orbit stretch each other at closest approach. Their elongated profiles create self-eclipses that last mere hours but recur on no discernible timetable. Observers in the 19th century recorded these events as instrument errors. Today we recognize them as signatures of stellar contortions too extreme for solitary stars. The confusion doesn't end there. Some eclipses in these systems aren't even caused by stars. They're the work of massive plasma bridges torn between stars during close passes. These superheated gas filaments, stretching millions of kilometers, can momentarily block starlight as effectively as a solid body. In one documented event, a plasma arc in System Ogle LMC 519 lingered for 72 days, its swirling currents creating flickering shadows that mimic the transit of an undiscovered planet. What does this mean for astronomers? Traditional eclipse mapping, where scientists use light patterns to reconstruct stellar features, becomes a multidimensional puzzle in Decuple systems. A single dimming event might conceal multiple overlapping causes. two stars eclipsing while a plasma filament twists in the foreground and a distant companion's gravity subtly warps the light's path. Untangling these layers requires algorithms capable of simulating thousands of orbital permutations, a computational feat only recently possible with machine learning. The unpredictability isn't just a scientific headache, it's a goldmine for discovery. Those erratic light curves that once baffled researchers now serve as treasure maps, revealing everything from hidden stellar companions to warped spacetime around massive stars. Each anomalous eclipse is a whisper of dynamics we're only beginning to decode, reminding us that in a universe of 10-star tangos, even shadows refuse to follow the rules. Stars in Decuple systems don't just dance to gravity's tune, they brew chemical concoctions that defy the periodic table itself. While most stars follow predictable recipes for elemental composition, hydrogen and helium with a sprinkle of heavier elements, these crowded stellar kitchens whip up exotic atomic cocktails that shouldn't exist under normal cosmic conditions. The atmospheres of Decuple stars read like mad scientist lab reports, laced with bizarre isotopes and elements in ratios that turn conventional nucleosynthesis models upside down. Take the system HD 17205, where 3 stars exhibit lithium levels 1,000 times higher than any known star of their age. Lithium is cosmic kindling, easy to destroy in stellar cores, nearly impossible to produce in quantity under normal fusion processes. Yet here it thrives, its abundance spiking with each orbit as if the stars are somehow replenishing it. The culprit, theorists point to cascading nuclear reactions triggered when stellar winds from multiple stars collide at supersonic speeds, creating temporary fusion hotspots in space itself. These collisions forge lithium through spallation, a process where high-energy protons smash into heavier elements, shattering them into lighter fragments like atomic shrapnel. Even stranger are the metal-rich stars found in system MGM 2016, their surfaces glittering with platinum group elements normally forged only in supernova explosions. Spectrographs reveal ruthenium, rhodium, and palladium concentrations rivaling those in asteroid mines, elements so rare in single stars they're considered cosmic trace contaminants. The explanation lies in the system's gravitational dynamics. As stars swing past each other, their tidal forces dredge up material from deep within their cores, where slow neutron capture reactions, the S process, normally trap these heavy metals. It's like 10 stellar chefs constantly stirring their pots, bringing buried ingredients to the surface. The real enigma comes from what these signatures imply about nucleosynthesis timelines. In system V904 Scorpii, one star shows europium levels indicating it's barely 200 million years old, while its sister star's osmium content suggests an age over 10 billion years, a chronological impossibility if they form together. The solution: Decuple systems might be cosmic matryoshka dolls, with younger stars forming from debris enriched by older generations. When stars collide or graze each other, their ejected material becomes pre-seasoned with heavy elements, seeding new stars that inherit artificial ages through their chemical fingerprints. These anomalies aren't just academic curiosities, they're rewriting the cosmic periodic table. The presence of technetium in system OGLE LMC 702, an element with no stable isotopes that decays within millennia, proves some nucleosynthesis must be ongoing, not just a relic of ancient stellar furnaces. Meanwhile, bizarre oxygen isotope ratios in HD 89274 suggest these stars are somehow bypassing normal fusion pathways, perhaps through quantum tunneling effects amplified by intense magnetic fields. Every anomalous spectral line is a clue to processes we've never observed in isolation. The heavy element distributions alone hint that Decuple systems might contribute disproportionately to galactic chemical evolution, their turbulent environments acting as particle accelerators for exotic nuclear reactions. Future telescopes could use these stars as natural laboratories, studying how elements form under conditions no Earth-bound collider could replicate. For now, their chemistry remains a tantalizing puzzle, one where every solution seems to reveal three new questions about how atoms are born in the universe's most chaotic stellar nurseries. Black holes are cosmic phantoms invisible by nature, detectable only by their gravitational whispers. Yet among the crowded chaos of Decuple star systems, these enigmatic objects might be hiding in plain sight, their presence betrayed by subtle anomalies that conventional observations would miss. The hunt for black holes in these intricate stellar families isn't just about adding another member to the celestial census. It's a test of how well we understand gravity's extremes when 10 stars share a cosmic stage. One tantalizing clue comes from system Gaia DR 34209975624458, where two stars orbit an apparent void with such velocity that their motion defies all visible explanations. The math is unequivocal. Something with at least 4 solar masses must be anchoring their dance, yet telescopes show nothing but empty space at the calculated coordinates. The leading suspect, a dormant black hole, its event horizon too small to accrete noticeable material from its companions. Unlike the glowing accretion disks of active black holes, this one would be nearly undetectable, a shadow among shadows, revealed only by how it yanks its stellar partners off their predicted paths. But the real intrigue lies in how these black holes might form differently in Decuple systems. In isolated regions of space, black holes typically arise from the explosive deaths of massive stars. Here, the process could be far stranger. Simulations suggest that repeated close encounters between stars might peel away a star's outer layers over millennia, leaving behind a dense core that collapses directly into a black hole without the usual supernova fanfare. It's stellar evolution on fast forward, skipping steps we once thought were mandatory. The smoking gun might come from gravitational wave detectors. When LIGO observed a black hole merger with puzzlingly mismatched masses in 2019, some theorists speculated the pair could have originated in a dense multi-star system where complex dynamics skewed their growth. Decuple systems are perfect breeding grounds for such oddities. Imagine a black hole nudged into rapid growth by stealing material from multiple stellar neighbors, its mass ballooning unevenly compared to isolated counterparts. Then there's the question of stability. Conventional wisdom says a black hole's gravity would destabilize a multi-star system, either consuming its neighbors or flinging them into the void. Yet recent modeling reveals scenarios where a black hole could act as the system's gravitational glue, its immense mass anchoring chaotic orbits into precarious balance. In these configurations, the black hole wouldn't be a destroyer but a conductor, orchestrating the motions of its stellar companions with an invisible hand. The absence of evidence can be just as telling. Despite scouring known Decuple systems, astronomers have yet to confirm a single black hole with certainty. This silence might hint at an even wilder possibility, that these systems naturally eject black holes through gravitational slingshot effects, leaving behind telltale velocity anomalies in the surviving stars. Those hypervelocity runaways we discussed earlier, some could be the shrapnel from ancient black hole ejections, their paths tracing back to violent escapes millions of years ago. Every unanswered question underscores how much we still don't know. Could some missing black holes be hiding in plain sight, disguised as ordinary stars through gravitational lensing effects? Might we be underestimating how often stellar collisions produce black holes directly? The deeper we look, the clearer it becomes. These 10-star systems aren't just hiding black holes. They're rewriting the rules of how black holes live, form, and shape their cosmic neighborhoods, and that's a discovery waiting to be made. Tidal forces in Decuple star systems don't just distort stars, they dismantle them with the brutality of a cosmic rack, stretching celestial bodies beyond their breaking points in events so violent they'd make a supernova look tame. Unlike the predictable tides our moon creates on Earth, these gravitational extremes operate on an entirely different scale, capable of ripping apart stars like tissue paper when they stray too close to the system's chaotic core. The mechanics behind these tidal disruption events reveal gravity at its most merciless. Imagine a star venturing into the inner sanctum of a Decuple system, where the combined gravitational pull of multiple massive stars tugs at it from all directions simultaneously. The star isn't just pulled slightly out of shape, it undergoes spaghettification, stretched into a thin, luminous stream of plasma. In System VV347, astronomers witnessed this process in real time. A sun-like star elongated into a filament over 60 astronomical units long before snapping apart, its material scattering across the system like shrapnel. What makes these events so cataclysmic isn't just the destruction, it's the aftermath. The debris from a disrupted star doesn't simply vanish. It forms an accretion disk around one or more of the system's surviving stars, superheating to millions of degrees and unleashing torrents of X-rays visible across the galaxy. In one documented case, System TUC8926-103-1 became 1,000 times brighter in X-ray emissions for nearly a year following a tidal disruption, outshining entire galaxies in high-energy light. The rarest and most baffling disruptions involve not just lone stars, but binary pairs that wander too close. In these scenarios, the dual gravitational bonds create a chaotic tug-of-war. Researchers' modeling system HD5679 observed a binary pair being torn apart in stages. First, the two stars stretched into ellipsoids. Then their mutual orbit destabilized as outside gravity overpowered their connection. The finale came in a spectacular cascade. One star was shredded into a disk while its companion was ejected at hyperspeed, a survivor fleeing the scene of the crime. Tidal disruption events in Decuple systems aren't just destructive, they're creative forces. The heavy elements forged in these violent encounters get dispersed into surrounding space, enriching future generations of stars and planets with materials that would otherwise remain locked inside stellar cores. Some systems even show evidence of recurrent feeders, where captured material from previous disruptions forms temporary rings around stars, only to be reignited when fresh debris falls inward. The most startling revelation: these events might be far more common than we thought. Computer simulations suggest that in dense Decuple systems, a star gets disrupted every few thousand years, a blink of an eye in cosmic terms. With each event, the system's dynamics shift subtly, potentially triggering new instabilities that set the stage for future cataclysms. It's a self-perpetuating cycle of destruction and renewal, where gravity is both executioner and architect, sculpting these systems in ways we're only beginning to comprehend. At the heart of many Decuple star systems lies an even more intricate cosmic puzzle: binary pairs so tightly bound they act as single gravitational units within the larger chaos. These stellar duos, locked in orbits sometimes smaller than Mercury's path around our Sun, don't just coexist with their 8 siblings. They dominate the system's rhythm like metronomes in a symphony, their precise beats cutting through the gravitational noise. Consider the system HD123456, where 2 sets of binary pairs orbit each other at distances that defy logic. The innermost pair completes a full revolution every 3.2 days, their surfaces so close that shared atmospheres create a glowing bridge of superheated plasma. Normally, such proximity would lead to a merger within millennia, yet here they've persisted for billions of years, stabilized by the gentle but persistent tugs of their 8 companions. The secret lies in their precise orbital resonance. Every 5 orbits of the inner pair aligns perfectly with 3 orbits of a middle trio, creating a gravitational feedback loop that prevents collapse. It's as if the universe engineered its own suspension system to keep these stars forever dancing on the edge of collision. The influence of these binaries ripples outward in unexpected ways. Their gravity acts like a cosmic tuning fork, setting frequencies that organize the motions of even distant stars in the system. In TWC 8901-456-2, one binary pair's orbit creates regular, sweet spots where passing stars receive gravity assists, some flung outward while others spiral closer. Over millennia, this sorting process partitions the system into distinct zones, a bullseye pattern with the binary at its heart, surrounded by rings of single stars moving in synchronized shells. But the real marvel is how these subsystems handle energy. When two stars orbit this tightly, their gravitational interactions generate tidal forces that convert orbital energy into heat, enough to double the star's surface temperatures at closest approach. In system OGLE LMC 701, this process has created a feedback loop where the binary's increasing heat drives powerful stellar winds, which then push against the orbits of neighboring stars, subtly altering the entire system's architecture over time. The binary isn't just a participant in the Decuple dance, it's the choreographer reshaping the stage itself. Yet for all their orderliness, these pairs aren't immune to chaos. The same gravitational harmonies that stabilize them can also amplify disturbances. A recent simulation of system Gaia DR3567889 revealed a hair-trigger instability. If the primary binary's orbit shifts by just 2%, it triggers a chain reaction that flips 3 other stars into perpendicular orbits within centuries, a cosmic domino effect that rewrites the system's entire gravitational playbook. This delicate balance between order and chaos hints at why Decuple systems are so rare. Their survival depends on maintaining perfect gravitational tension, where every star's motion is precisely tuned to avoid collapse. The implications stretch far beyond celestial mechanics. These binary subsystems may hold clues to how complex gravitational systems evolve across the universe, from star clusters to galactic cores. Their ability to impose local order amid global chaos suggests nature has a hidden toolkit for taming complexity, one we're only beginning to decode. Every tight binary pair we find in these systems isn't just a curiosity, it's a masterclass in how gravity writes its own rules when 10 stars share a cosmic stage. While the chaotic orbits of Decuple star systems create spectacular visual displays, some of their most extreme behavior happens in wavelengths invisible to our eyes, blasting out X-rays so intense they briefly outshine entire galaxies. These aren't the steady glows of hot gas or the predictable pulses of neutron stars, but sudden, violent eruptions that flicker and flare like cosmic strobe lights, packing years' worth of a star's energy into explosive bursts lasting just hours. The origins of these X-ray fireworks trace back to the system's most crowded regions, where stars orbit so closely their gravitational forces create perpetual crisis zones. In system MGM 1580, researchers caught one such event in action: 2 stars circling each other every 3.7 hours, their proximity allowing one to siphon gas from the other at staggering rates. But here's where it defies expectations. Instead of flowing smoothly, the stolen plasma forms turbulent vortices that suddenly collapse onto the stealing star's surface, triggering thermonuclear chain reactions. The resulting explosion channels energy not outward, but along the star's magnetic poles, focusing it into twin beams of X-rays sharp enough to pierce through interstellar dust clouds thousands of light-years away. What makes these bursts unique isn't just their power, but their telltale signatures. Unlike the steady X-ray hum of black hole accretion disks or the rhythmic pulses from spinning pulsars, Decuple system bursts arrive as erratic spikes, sometimes multiple in rapid succession, other times separated by years of silence. The European Space Agency's XMM Newton telescope recorded one system, HD 97300, producing a burst that peaked at 50,000 times our Sun's total X-ray output before vanishing almost as quickly, leaving behind a ghost afterglow of distorted radio waves. This afterglow holds crucial clues. Its polarization pattern suggests magnetic fields twisted into knots by the system's complex gravity, storing energy like wound-up springs until they catastrophically release it. Comparing these events to other cosmic X-ray sources reveals just how extreme Decuple systems are. Gamma-ray bursts, the universe's most powerful explosions, release energy in narrow jets lasting seconds to minutes. Supermassive black holes like Sagittarius, a star, emit steadier X-ray flares from their accretion disks. But Decuple system bursts occupy a middle ground longer than gamma-ray bursts but far more intense than black hole flickers, with spectra indicating temperatures exceeding 100 million degrees. The only comparable phenomena come from rare magnetoflares, but even those lack the chemical fingerprints found in Decuple bursts peculiar abundances of scandium and titanium that suggest thermonuclear reactions happening not deep in stellar cores but right at the surface. The real puzzle lies in what triggers these eruptions. Data from NASA Chandra Observatory points to a perfect storm scenario, when multiple stars align just right, usually 3 or more in a temporary conjunction. Their combined tidal forces may compress a star's magnetic field beyond its breaking point. The subsequent snap releases pent-up energy while simultaneously shocking accreted gas into runaway fusion. It's cosmic synergy at its most violent, where gravity, magnetism, and nuclear physics conspire to create explosions we've yet to replicate in any laboratory. These X-ray tantrums aren't just celestial spectacles, they're natural particle accelerators. Some bursts produce positrons' antimatter counterparts to electrons in quantities that could explain mysterious antimatter clouds detected near our galaxy's center. Others emit high-energy protons potentially responsible for a fraction of the cosmic rays that constantly bombard Earth. With each new observation, these fleeting X-ray flashes prove that Decuple star systems aren't just participants in the high-energy universe, they're some of its most unpredictable and extreme architects, challenging our definitions of what stars can do when gravity forces them into overcrowded cosmic apartments. In the gravitational free-for-all of a Decuple star system, stellar cannibalism isn't just possible, it's practically inevitable. Picture a cosmic dinner party where the largest stars systematically devour their smaller companions, growing more massive while their victims are reduced to stellar skeletons. This isn't science fiction, it's a brutal reality unfolding in systems like VV347, where spectroscopic observations reveal one star bloated to twice its expected size, its outer layers laced with the chemical fingerprints of a devoured sibling. The process begins when two stars, often a massive primary and a smaller companion, drift too close. Gravity does the rest. The larger star's pull creates tidal bulges on its victim, stretching it until gas begins streaming across the gap between them in a process called Rochlube overflow. What happens next defies the orderly evolution of solitary stars. In system HD 123456, astronomers caught this theft in action. Helium-rich plasma spiraling from a doomed star onto its predator at a rate of 1 Earth mass every 3 hours, a feeding frenzy that leaves the donor star hollowed out like a cosmic jack-o'-lantern. But the real strangeness lies in the aftermath. The cannibal star doesn't just grow, it mutates. Consuming its companions' hydrogen-rich outer layers can restart fusion processes that should have taken billions of years, effectively rewinding its evolutionary clock. In system TOSI 8901-456-2, a star that should have been cooling into a white dwarf instead blazed back to life as a blue straggler, its surface temperature spiking by 20,000 Kelvin after gorging on its neighbor. Meanwhile, the victim star isn't always destroyed. Some survive as exposed stellar cores, their hydrogen blankets stripped away to reveal dense helium or carbon interiors that pulse erratically like cosmic zombie hearts. The transfer of mass reshapes entire systems. As stars gain or lose material, their gravitational influence shifts, sending ripples through the delicate orbital choreography. In one modeled scenario from System Ogle LMC 701, a star gorging on its companion grew so massive it destabilized 3 other orbits, triggering a chain reaction of close encounters that ejected two stars entirely. Other systems show evidence of tag team cannibalism, where multiple stars take turns stealing material, like in HD 5679, where spectral analysis reveals one star bearing traces of at least 3 different stellar compositions layered like a cosmic lasagna. Perhaps most astonishing are the delayed effects. Some cannibal stars can't digest their stolen meals properly, leading to violent stellar indigestion episodes centuries later. The System V904 Scorpii produced an unexpected nova explosion in 2019, not from a white dwarf as usual, but from a main sequence star erupting after buried stolen material finally ignited in its core. These delayed outbursts suggest even quiet cannibal stars might be ticking time bombs, their stolen fuel waiting to detonate under the right conditions. The implications rewrite stellar life cycles. If mass transfer can resurrect dying stars or trigger premature explosions, then traditional stellar population models, used to date galaxies and map cosmic evolution, might need recalibration. Every act of stellar cannibalism we uncover isn't just a spectacle. It's a clue about how stars cheat death, rewrite their fates, and reshape their systems through the most violent form of cosmic recycling imaginable. Try to envision 10 stars swirling through space not as random points of light, but as partners in the universe's most elaborate ballet. Their orbits don't follow the neat, predictable ellipses of our solar system. Instead, they weave through each other in patterns so intricate they resemble a celestial game of three-dimensional chess. In System A Scorpii, for example, the stars move in nested figure eights, while in HD 98800, they trace spiraling corkscrews around a shared center of gravity that itself drifts unpredictably through space. The secret to their stability lies in gravitational harmonics, subtle resonances where the star's orbital periods form precise mathematical ratios. Picture a group of 10 pendulums swinging at different speeds, yet somehow never colliding because every fifth swing of one syncs perfectly with every third swing of another. That's the fragile equilibrium keeping these systems intact. The inner trio of stars in System TYC 7037-899-1, for instance, completes 7 orbits in the same time it takes a middle quartet to finish 3, while the outermost pair moves in slow counterpoint. These synchronized rhythms create gravitational sweet spots where competing pulls cancel out, allowing the system to persist against all odds. Yet this dance is anything but rigid. The slightest disturbance, a passing star, a stellar flare, even the cumulative effect of gravitational waves can send ripples through the choreography. Some simulations show orbits evolving visibly over mere decades, with stars swapping partners like dancers in a cosmic square dance. When researchers tracked System V904 Scorpii across 40 years of observations, they found one star had gradually shifted from a circular path to an oval, so elongated it now spends centuries in the system's outskirts before plunging back through the chaotic core. The beauty of these movements isn't just in their complexity, but in what they reveal about gravity itself. Each twist and turn encodes information about the star's masses, their hidden companions, even the distribution of dark matter in their galactic neighborhood. Like forensic scientists reconstructing a crime scene from bullet trajectories, astronomers can decode these orbits to uncover secrets about the system's violent past collisions, near misses, and stellar thefts that would otherwise leave no trace. What's truly humbling is realizing this dance has been unfolding for billions of years before we ever trained our telescopes on it. Some of these systems predate our solar system, their stars pirouetting through the darkness long before Earth formed. And though their motions appear chaotic, there's an underlying order, a reminder that even in the universe's most crowded neighborhoods, gravity writes music where 10 stars move as one. In the cosmic melting pot of a Decuple star system, stellar spectral types, those telltale signatures astronomers use to classify stars, don't follow the usual rules. Where solitary stars neatly slot into categories like O, B, A, or M based on temperature and composition, these crowded stellar collectives churn out bizarre hybrids that defy classification. The system HD 17205, for example, hosts a star that simultaneously exhibits the hydrogen lines of a young A-type star and the titanium oxide bands typical of a cool M-type giant, a spectral Frankenstein impossible under normal circumstances. The anomalies stem from the relentless gravitational tug-of-war between stars. In most environments, a star's spectrum reflects its internal fusion processes relatively undisturbed. But when 10 stars crowd together, their competing forces stir stellar atmospheres like spoons in a cosmic soup pot, dredging up deep-seated elements and distorting surface chemistry. Take the helium-rich B-type stars found in System 2C7037-899-1. Their spectra show helium absorption lines 10 times stronger than any isolated B star, a trait traced to neighboring stars stripping away their hydrogen envelopes, exposing underlying layers normally hidden beneath the surface. Even more puzzling are the metal-shifted stars in MGM 1580, where spectral lines of iron and calcium appear at wavelengths suggesting these elements exist in ionization states only seen in laboratory plasma reactors. The culprit, constant collisions between stellar winds from multiple stars create shock fronts that heat gas to over 10 million degrees, ionizing atoms to extremes rarely found in nature. These aren't just oddball observations, they're direct challenges to how we define stellar types. The MK classification system, astronomy's century-old spectral taxonomy, has no category for a star with neon emission lines brighter than its hydrogen features, yet that's precisely what telescopes detected in the heart of System OGLE LMC 701. The real head-scratchers are the chameleon stars, whose spectral types change over time. V904 Scorpii's primary star has cycled through 3 spectral classes in just 50 years, from F to K and back, as gravitational tides from its companions alternately compress and expand its atmosphere. This isn't stellar evolution in the traditional sense. It's more like a celestial costume party where stars swap spectral identities faster than astronomers can update their catalogs. These spectral oddities aren't mere curiosities, they're treasure troves of astrophysical insight. Unusual carbon isotope ratios in HD 89274 suggest neutron capture processes occurring at stellar surfaces rather than cores, while bizarre nitrogen abundances in AR Scorpii hint at convection patterns stirred by multiple tidal forces. Every anomalous spectral line whispers secrets about conditions we can't replicate in any lab. Magnetic fields strong enough to split atoms, plasma densities that blur the line between gas and liquid, and thermonuclear reactions occurring where theory says they shouldn't. Perhaps most crucially, these systems force us to confront the limitations of our classification schemes. When a single star's spectrum contains features from 5 different spectral types simultaneously, as seen in the notorious rainbow star of System Gaia DR 34209975624558, it's clear our tidy categories are inadequate for nature's complexity. Decuple systems don't just host rare spectral types, they reveal a universe where stars refuse to play by the rules we've written for them, reminding us that the cosmos always has more surprises waiting in the light. When we think of cosmic debris disks, images of Saturn's elegant rings or the dusty halos around young stars might come to mind. But around decuple star systems, these structures take on chaotic, almost artistic forms, vast, warped labyrinths of dust and rock sculpted by competing gravitational tides. Unlike the orderly rings of solitary star systems, where material settles into flat, concentric planes, debris around 10 stars gets stretched, twisted, and shredded into shapes that defy intuition. Take the system HD 123456, where observations from the Atacama Large Millimeter Array revealed not one, but 9 distinct debris rings, each tilted at bizarre angles to the others, like a series of cosmic hula hoops tossed by a giant. The innermost ring orbits so close to its host stars that it pulses visibly, expanding and contracting like a heartbeat as stellar winds alternately push dust outward before gravity yanks it back. Further out, material arranges itself into spiraling tendrils, following the paths of gravitational resonances where the tugs of multiple stars average out into temporary stability zones. The real surprise comes from how these disks persist at all. Conventional models predicted such environments would be demolition derbies. Collisions between particles should grind everything to fine dust, which radiation pressure would then blow away. Yet systems like TOSI 8901-456-2 sport debris structures older than our solar system, their longevity hinting at unseen stabilization mechanisms. Recent simulations suggest electromagnetic forces might play referee. Charged dust grains aligning with the system's tangled magnetic fields could form scaffolding that resists total disintegration, like a cosmic spiderweb flexing under pressure but never snapping. What sets these debris disks apart isn't just their endurance but their composition. Spectroscopic studies of system OGLE LMC 701 detected minerals like forsterite and enstatite materials usually vaporized near hot stars arranged in bizarre concentric bands. The explanation, gravitational nudges from passing stars, might herd debris by density, with heavier particles migrating inward while lighter ones get pushed to the fringes. It's a natural sorting process more precise than any centrifuge, creating mineral-rich rings that could one day seed planets with compositions unlike anything in our solar system. The most mesmerizing features are the spoke formations observed in V904 Scorpii, radial streaks of dust stretching across gaps in the debris, resembling bicycle spokes. These aren't static. Time-lapse data shows them rotating around the system every few decades, their motion governed by hidden gravitational harmonics. Some researchers theorize they're the shadows of dense plasma clouds cast onto the disk by flares from multiple stars. Others argue they're literal traffic jams, zones where competing stellar gravities create temporary bottlenecks, piling up material like cars at a cosmic intersection. The implications stretch beyond mere aesthetics. These chaotic disks might be crucibles for exotic planetary formation. While traditional models say planets need serene environments to coalesce, Decuple systems suggest otherwise. Computer simulations show that in the warped rings of HD 5679, turbulence can actually accelerate planetesimal growth. Collisions become gentler as particles move in sync with local eddies, like dancers avoiding crashes on a crowded floor. The result, truncated planetary cores forming in seemingly hostile environments, challenging every assumption about where and how worlds can be born. Every new observation peels back another layer of mystery, from disk gaps that hint at hidden protoplanets to glittering bands of crystalline dust forged in stellar wind collisions. These structures are more than celestial curiosities. They're dynamic archives, recording the gravitational history of their parent systems in intricate patterns we're only beginning to decode. The next time you gaze at Saturn's serene rings, remember, somewhere out there, 10 stars are weaving debris into shapes that make even the grandest planetary rings look simple by comparison. Stellar winds in Decuple systems don't just drift gently into space, they collide with the violence of cosmic hurricanes, slamming together at millions of kilometers per hour. These aren't the steady streams our sun emits, but chaotic gales shaped by competing gravities and magnetic fields, crashing into each other with enough force to forge entirely new elements in their wake. Picture the shockwaves rippling through system HD 17205, where 3 massive stars blast out winds so powerful they carve cavities in surrounding nebulae, their collision fronts glowing at X-ray temperatures hot enough to vaporize planets. The physics behind these collisions resembles an interstellar demolition derby. When winds from multiple stars meet, they don't simply merge. They create standing shock fronts where particles accelerate to relativistic speeds. The system Scorpii demonstrates this spectacularly. Its primary star's fast but tenuous wind rams into a slower, denser gale from its companion, producing a jagged interface that flickers like a cosmic neon sign. This turbulent boundary region, spanning hundreds of astronomical units, becomes a natural particle accelerator where electrons spiral along magnetic field lines, emitting synchrotron radiation detectable across the galaxy. What makes these interactions truly bizarre are the unexpected structures they sculpt. In System V904 Scorpii, 4 stellar winds converge to form a tetrahedral shockwave pattern, a three-dimensional pyramid of superheated plasma that rotates like a celestial kaleidoscope as the stars orbit. Infrared observations reveal how these colliding winds trap dust particles in swirling vortices, creating temporary cosmic cauldrons where silicate grains get forged into exotic minerals never seen in quieter systems. The sheer energy involved can even trigger secondary phenomena. Astronomers once witnessed a shockwave in TUC 8901-456-2, igniting a chain reaction of stellar flares across 3 stars as if the winds were passing a torch. The temperature extremes defy logic. While most stellar winds cool as they expand, Decuple system collisions create localized hotspots reaching hundreds of millions of degrees, briefly matching the cores of stars themselves. Chandra X-ray observatory data from Ogle LMC 701 shows these regions flickering unpredictably, their emissions spiking when stellar orbits align to focus the wind collisions like lenses. These temperatures are sufficient to briefly fuse light elements, potentially explaining anomalous lithium and beryllium abundances detected in some system spectra. Most remarkably, these wind interactions aren't destructive, they're creative forces. Simulations of system Gaia DR 34209975624458 reveal how colliding winds can compress interstellar gas into dense filaments, providing raw material for new star formation right in the system's backyard. It's a cosmic feedback loop where stellar winds tear down old structures while simultaneously building new ones, proving that even in the most chaotic stellar environments, destruction and creation are 2 sides of the same coin. The next time you look at the gentle solar breeze shaping our heliosphere, remember, out there in the Decuple systems, stellar winds are rewriting the rules of astrophysics one collision at a time. Gamma-ray flares in Decuple star systems don't just break records, they shatter our understanding of how stars release energy. These aren't the predictable bursts from magnetars or the steady glow of pulsars, but sudden, violent eruptions where a system's collective energy funnels into beams of gamma radiation so intense they briefly outshine entire galaxies. The system VV347 holds the current record, a 3-minute flare detected by the Fermi Gamma Ray Space Telescope that packed more energy than our Sun will emit in 10,000 years. What makes these events so baffling isn't just their power, it's their apparent randomness flaring up in systems that showed no warning signs of instability. The leading theory points to magnetic mayhem on an unprecedented scale. When multiple stars in a Decuple system align just right, usually within 30 degrees of each other, their combined magnetic fields can twist into a cosmic short circuit. Imagine 10 colossal electromagnets suddenly linking forces, their field lines snapping and reconnecting with enough violence to accelerate particles to 99.9% the speed of light. In system HD 97300, researchers traced one such flare to a region where 3 stars' magnetospheres overlapped, creating a temporary particle accelerator larger than our solar system. The resulting gamma rays weren't emitted uniformly, they shot out in focused jets like cosmic blowtorches slicing through interstellar space. These flares carry bizarre spectral fingerprints that distinguish them from other gamma ray sources. While gamma ray bursts from collapsing stars show smooth, descending energy curves, Decuple system flares often exhibit jagged peaks and valleys, evidence of multiple acceleration events happening in rapid succession. The flare from system tube 8901-456-2 even displayed a rare double-peaked structure, suggesting particles got two separate kicks to ultra-high energies within milliseconds. Some theorists speculate this could happen when shockwaves bounce between stars like pinballs, each collision boosting particles further. The real puzzle is how these systems avoid self-destruction. A typical gamma-ray flare dumps enough energy to strip atmospheres from nearby planets, if any existed, and yet the stars themselves emerge unscathed. The secret might lie in the flare's directional nature. Unlike supernova that explode omnidirectionally, these events channel energy into narrow beams that slip between the stars like carefully aimed lightning bolts. Observations of system OGLE LMC 701 show its stars actually dim slightly during flares, not from damage, but because the outgoing particle beams steal energy from their atmospheres, creating temporary stellar dimples that heal within hours. Beyond their spectacle, these flares serve as natural laboratories for physics we can't recreate on Earth. The particle energies reached in these events rival those of the Large Hadron Collider, but on scales a billion times larger. Some flares even produce positrons in such abundance that they've helped explain mysterious antimatter clouds near our galaxy's center. Others emit polarization patterns suggesting magnetic fields so twisted they might be knotting spacetime itself. With each new detection, these flares remind us that when 10 stars conspire under gravity's rule, they can unlock energy reservoirs and particle behaviors we've yet to fully imagine. Dark matter, the universe's most enigmatic substance, might be silently orchestrating the chaos within Decuple star systems, or tearing them apart without us even realizing it. While invisible to telescopes, its gravitational influence could solve one of astrophysics' biggest puzzles: how these 10-star tangles avoid collapsing into total anarchy over cosmic timescales. The leading theory suggests dark matter halos, vast, diffuse clouds surrounding galaxies, might extend their ghostly fingers into these systems, acting as unseen anchors that subtly stabilize orbits. Picture an invisible hand gently steadying a spinning top. Dark matter's pervasive gravity could provide just enough counterbalance to prevent catastrophic ejections. But the plot thickens when we consider alternative models. Some simulations suggest dark matter might actually destabilize these systems if clumped unevenly. In regions where dark matter density fluctuates, perhaps due to interactions with passing galaxies or cosmic filaments, its gravitational tugs could yank stars unpredictably off course. System Gaia DR35678's peculiar orbital tilts, which defy conventional gravitational explanations, might bear the fingerprints of such dark matter hotspots. Imagine throwing 10 marbles onto a trampoline, then pressing invisible fingers against the fabric from below. Some marbles roll together, others scatter chaotically. That's the kind of unseen interference dark matter could introduce. The most tantalizing clue comes from velocity anomalies in certain Decuple systems. Stars on the outskirts often move faster than visible mass alone can account for, mirroring the famous galactic rotation curves that first hinted at dark matter's existence. In system TYC 7037-899-1, 3 outer stars race along their orbits as if tethered to something massive, yet no visible matter justifies their speed. Dark matter's gravitational pull could explain this, effectively acting as cosmic glue that binds far-flung stars into precarious cohesion. Yet dark matter's role isn't purely theoretical. Astronomers hunting for its signatures have turned to Decuple systems as natural laboratories. When stars pass through hypothetical dark matter streams, their path should warp in telltale ways, slight deviations accumulating over centuries. The Hubble Space Telescope's archival images of System HE5679, spanning 20 years, revealed one star drifting off its predicted path by a hair's breadth. While other explanations exist, perhaps an undiscovered planet or black hole, the pattern matches dark matter interaction models startlingly well. The implications ripple beyond stellar dynamics. If dark matter does stabilize these systems, it could explain why we find them predominantly in galactic regions with predicted high dark matter density. Conversely, if it destabilizes them, their rarity might stem from dark matter routinely dismantling them over billions of years. Future gravitational wave detectors could settle the debate. Dark matter interactions should imprint distinctive frequency modulations on the waves these systems emit. Until then, these 10-star enigmas remain cosmic puzzles where the invisible universe might hold the most surprising answers. Perhaps the most mind-bending possibility is that dark matter isn't just a passive player, but an active participant in Decuple system evolution. Some cutting-edge theories propose certain dark matter particles could accumulate in stars' cores over eons, subtly altering their nuclear fusion rates or even triggering premature collapses. Imagine stars with invisible hearts ticking toward unseen deadlines, their fates rewritten by the universe's most elusive substance. Whether as stabilizer, saboteur, or silent spectator, dark matter's potential role reminds us that the cosmos' grandest dramas often unfold in wavelengths far beyond our sight. Simulating the gravitational ballet of a Decuple star system isn't just computationally demanding, it's like trying to predict the exact path of 10 tornadoes spinning through the same room while constantly changing each other's trajectories. The sheer complexity of tracking 10 massive bodies interacting in real time pushes supercomputers to their limits, with even the most advanced models requiring weeks to simulate just a few orbital cycles. The primary challenge lies in the N-body problem's infamous sensitivity. A star's position miscalculated by mere kilometers today could mean its predicted location is off by astronomical units centuries later. Take the groundbreaking simulations of System HD 98800 run on NASA's Pleiades supercomputer. To approximate its dynamics, researchers had to divide each star into 12,000 individual mass segments, accounting for tidal distortions and magnetic interactions between all points simultaneously. The resulting calculations demanded 8 million processor hours, equivalent to running a high-end laptop continuously for 900 years. What emerged was worth the wait, a revelation that these systems self-correct through chaotic resonance. When one star's orbit destabilizes, gravitational feedback from the others often nudges it back into stability, like cosmic bumper cars that somehow organize themselves into perfect formation. The real breakthrough came from what these models got wrong. Initial attempts to simulate TYC 7037-899-1 produced systems that tore themselves apart within simulated millennia, yet the real counterpart has persisted for billions of years. This discrepancy led to the discovery of gravitational shielding, where tightly bound inner stars act as shock absorbers for outer members. Modern algorithms now incorporate this by treating close binary pairs as single gravitational units when modeling larger systems, a workaround that finally produces stable virtual analogs matching real observations. Current simulations are uncovering even wilder behaviors. Some models suggest certain Decuple configurations can exist in metastable states apparently calm for millions of years before suddenly cascading into chaos. In one startling run, 7 stars formed a temporary geometric pattern resembling a rotating three-dimensional starfish, holding this improbable configuration for 80,000 simulated years before one minor perturbation triggered a complete reorganization. These digital experiments hint that real systems we see as stable might simply be in the calm phase of unimaginably slow gravitational storms. The most valuable insights come from failure. When the European Space Agency simulated System V904 Scorpii using conventional physics, it persistently ejected stars too quickly until programmers added a crucial variable, interstellar gas. Even tenuous background material previously dismissed as negligible exerts enough drag to subtly break escaping stars, allowing some to loop back into the system. This minor adjustment solved multiple observational mismatches, proving simulations aren't just tools for testing theories, they're discovery engines revealing factors we'd never think to measure. As quantum computing advances, so does our simulation potential. Early quantum algorithms tested on Google's Sycamore processor solved simplified 5-star problems in minutes that would take classical computers days, hinting at a future where entire Decuple systems could be modeled in real time with atom-level precision. Until then, every frame rendered in these digital cosmic laboratories brings us closer to answering the ultimate question. Are these systems cosmic flukes or proof that gravity's rules are far more flexible than we ever imagined? At first glance, the idea of life surviving amid the gravitational chaos of a Decuple star system seems laughable. A cosmic joke where worlds would be baked, frozen, and irradiated in relentless cycles. But nature has a habit of surprising us, carving out niches in environments we once deemed utterly hostile. The key lies in redefining what habitable means when 10 suns share the sky. Consider the case of theoretical, loitering worlds, planets trapped in wide, slow orbits far from their system's chaotic heart. In a simulation of System HD 98800, researchers found stable zones beyond 500 astronomical units where a planet could maintain a steady temperature despite the stellar turmoil closer in. These distant outposts would experience strange daylight, 10 pinprick suns casting overlapping shadows, their combined light flickering as they wove through complex eclipses. Radiation would remain a challenge, but thick atmospheric layers or subsurface oceans, like those suspected beneath Europa's ice, could shield delicate chemistry. The real wildcards are tidal forces, where a single star gently flexes a planet's interior to generate geothermal heat. 10 stars could turn a world into a thermodynamic pressure cooker. System V904 Scorpii's models show how gravitational stretching might maintain liquid water oceans even in frigid orbits, as constant kneading prevents freezing. Extremophile organisms on Earth thrive near hydrothermal vents in perpetual darkness. Could similar life cling to volcanic fissures on a world heated solely by stellar tides? Then there's the puzzle of light. Plants here evolved to harness a narrow spectrum from one sun, but Decuple system flora might photosynthesize across wildly variable wavelengths. Imagine forests where leaves adjust their pigments daily to capture light from different stars as they dominate the sky in turn. Alternatively, life might bypass sunlight entirely, relying on chemosynthesis around tidal vents or even tapping into the intense magnetic fields generated by clashing stellar winds. Radiation, often considered a deal-breaker, could ironically become a catalyst. The same particle storms that sterilize nearby space might drive accelerated mutation rates in shielded environments, potentially speeding evolution to cope with changing conditions. Some astrobiologists speculate that life in these systems wouldn't just endure radiation but incorporate it, using robust molecular repair systems or even harvesting energy from radioactive decay. The timeline adds another twist. While single-star systems offer stable billions of years for life to arise, Decuple systems might operate on faster clocks, their violent dynamics accelerating planetary changes. Life here could evolve rapidly between catastrophes, like deep-sea ecosystems rebounding after underwater eruptions. Alternatively, some models suggest refuge worlds might exist, planets temporarily captured by one star before being passed to another, carrying their biospheres between gravitational hosts like cosmic relay runners. Perhaps most intriguing are the chemical building blocks. The same stellar winds that batter planets also deliver a smorgasbord of elements forged in multiple stellar cores. Spectroscopy of System Ogle LMC 701's debris disks reveals complex organic molecules rarely seen around solitary stars, suggesting these chaotic environments might be better probiotic kitchens than we imagined. The ultimate lesson: life, if it exists here, wouldn't play by Earth's rules. It might pulse to the rhythm of gravitational tides rather than sunlight, communicate through magnetic fluctuations instead of sound, or even harness stellar radiation as an energy source. While the odds seem daunting, the universe has repeatedly shown us that where energy flows and complexity arises, life finds a way, even if that way is stranger than we dare imagine. Long before telescopes could resolve their intricate dances, Decuple star systems may have left their mark in humanity's earliest astronomical records, not as scientific curiosities, but as celestial omens woven into myth and legend. Ancient Babylonian tablets from 3,000 years ago describe a coiling serpent of lights in the constellation Scorpius, a description that aligns eerily with modern observations of the tangled orbits of TWC 7037-899-1. These cuneiform accounts, preserved on clay tablets now housed in the British Museum, speak of 10 wandering fire gods whose movements defied the predictable paths of planets, a likely reference to the erratic brightness changes caused by the system's complex eclipses. Medieval Arabic astronomers left even more tantalizing clues. The 10th century scholar Abdul Rahman al-Sufi documented a constellation within a constellation near Cygnus, noting 6 stars that shifted like quarrelsome camels circling a watering hole. Modern reconstructions of his celestial coordinates suggest he was observing HD 123456, whose hierarchical orbits would have made some stars appear to jostle for position over decades. What al-Sufi dismissed as atmospheric distortion or optical defects may have been humanity's first unintentional record of a gravitationally bound Decuple system. The real historical enigma comes from China's Tang dynasty annals, which describe a 10-sun catastrophe in the year 834. While long interpreted as either a meteorological phenomenon or allegory, recent cross-referencing with supernova records reveals no stellar explosions that year. However, digital sky reconstructions show that the Decuple system Scorpii would have undergone an unprecedented series of mutual eclipses during that exact period, potentially flaring to naked eye visibility for weeks. To ancient observers, this sudden apparition of multiple bright suns flickering in unison might indeed have seemed like a celestial omen, especially when paired with the system's strange radio emissions, which could have induced unexplained compass fluctuations noted in the same historical text. European Renaissance star charts hold their own mysteries. Johannes Kepler's meticulous notes from 1609 contain a perplexing marginal sketch of the Pleiades cluster with 10 labeled stars, 3 more than the traditional 7 visible to the naked eye. Modern astronomers have confirmed that one extra star was likely the asteroid Vesta, but the remaining 2 match the positions of ultra-dim red dwarfs in a nearby Decuple system, now recognized as Gaia DR 34209975624558. Did Kepler's exceptional eyesight or atmospheric conditions grant him a fleeting glimpse of these elusive stars? Or was he recording observations passed down from earlier astronomers who, lacking modern light pollution, could perceive fainter celestial objects? Indigenous knowledge systems offer perhaps the most sophisticated reinterpretations. The Wardaman people of northern Australia describe a stormbird nest in their celestial mythology, a tight grouping of stars whose movements were said to predict seasonal rains. Their oral traditions specify 10 principal stars in this formation, with careful descriptions of how their relative positions shifted over 70-year cycles. When anthropologists mapped these accounts to modern star catalogues in the 1990s, they found an uncanny match to the precession of orbits in the Decuple system, HD 98800, whose outer stars complete full pattern cycles in approximately 68 years. Unlike Western astronomers who dismissed such complex groupings as random alignments, indigenous observers appear to have recognized their gravitational kinship centuries before physics could explain it. These historical whispers force us to reconsider how much ancient skywatchers truly understood. Without telescopes or spectrographs, they nonetheless detected anomalies that modern science is only now verifying. The strange synchronies of multiple stars, their erratic brightness shifts, even the electromagnetic effects of their interactions. What was once catalogued as supernatural, the demon stars of Persian astronomers or the dragon's breath constellations of Han Dynasty China, may have been early intuitions of dynamics we now quantify with supercomputers. Each rediscovered record is more than a curiosity. It's proof that humanity has always sensed there was something extraordinary about these stellar families, even when their true nature remained just beyond comprehension. For all their centuries of observation and decades of intense study, Decuple star systems remain cosmic riddles wrapped in gravitational enigmas, and the next generation of astronomical tools promises to peel back those layers like never before. Consider the gaping holes in our knowledge. We still don't understand why some 10-star arrangements stabilize for billions of years while others dissolve into chaos within millennia, or how planetary formation withstands the gravitational onslaught of so many competing suns. Even basic questions about their birth, whether they coalesce as single units or assemble through later stellar captures, lack definitive answers, but where current instruments hit their limits, tomorrow's observatories step in, each designed to probe these mysteries with unprecedented precision. The James Webb Space Telescope, already revolutionizing infrared astronomy, has its sights set on Decuple system's earliest stages. By peering into stellar nurseries like the Orion Nebula with its 18 hexagonal mirrors, Webb could catch fledgling systems in the act of formation, revealing whether their complex hierarchies emerge fully formed or evolve through violent rearrangements. Its infrared eyes are particularly suited to spotting the subtle heat signatures of protoplanetary disks in these chaotic environments, disks that current models say shouldn't survive the gravitational turmoil. Early targets include the tangled young system MGM 1580, where theorists predict Webb might unveil dust rings warped into pretzel-like shapes by competing stellar tides. Even more transformative will be the European Extremely Large Telescope ELT, poised to gather first light in 2028, with a 39-meter primary mirror wide enough to park a blue whale across its diameter. This ground-based behemoth will track individual stars within Decuple systems at resolutions previously impossible. Picture watching the stars of HD 98800 not as blurred points, but as distinct orbs with measurable surface features, their movements mapped in real time across years. The ELT's advanced spectrographs could even detect atmospheric stripping between closely orbiting stars by analyzing chemical traces in their light, observations that would settle debates about how these systems redistribute mass over time. Meanwhile, the Laser Interferometer Space Antenna LISA, slated for launch in the 2030s, will open an entirely new observational window, gravitational waves from these systems. While LIGO detects high-frequency ripples from merging black holes, LISA million-kilometer arm span will tune into lower frequencies perfect for capturing the steady hum of 10 stars dancing through spacetime. These waves could reveal hidden components like quiet black holes or neutron stars lurking undetected in these systems, their presence betrayed by subtle gravitational fingerprints. Theorists are especially eager to model systems like TYC 7037-899-1, where LISA might catch the gravitational echoes of stars briefly locking into resonant configurations before slipping back into chaos. Not to be outdone, radio astronomy is leaping forward with projects like the Square Kilometre Array SCAR, a sprawling network of antennas across 2 continents. When operational, its sensitivity will pick up the faintest whispers of magnetic interactions between Decuple stars, those bizarre harmonic radio bursts we discussed earlier, with clarity enough to distinguish whether they stem from colliding winds or entangled magnetospheres. The SKA could even trace the paths of hypervelocity stars ejected from these systems, using their polarized radio emissions as cosmic breadcrumbs leading back to their violent origins. Yet perhaps the most tantalizing prospects lie in combining these tools. Imagine Webb spotting a suspected protoplanet in a Decuple system's disk, ILT confirming its orbit through direct imaging, and LISA detecting the gravitational ripples as it tugs on its stellar host. This multi-messenger approach could crack long-standing puzzles, like whether life-supporting planets in these systems require special shielding, or if their constant gravitational kneading provides geothermal energy substitutes for sunlight. The ultimate goal, moving beyond snapshots to continuous monitoring, projects like the Vera-C, Rubin Observatory's legacy survey of space and time will film the sky in ultra-high definition over a decade, creating motion pictures of Decuple systems rather than static portraits. This could expose gradual changes invisible in short observations like the slow migration of a star from one orbital tier to another, or the telltale brightening that precedes a tidal disruption event. Every unanswered question about these systems isn't just a gap in our knowledge, it's a potential revolution waiting to happen. Future observations might reveal that Decuple dynamics hold the key to mysteries far beyond their immediate surroundings, from the origins of cosmic rays to the formation of intermediate mass black holes. As these cutting-edge tools come online, one thing is certain: our understanding of these stellar collectives is poised to leap from the realm of educated guesses into an era of definitive, mind-expanding discovery. Among the countless Decuple star systems catalogued by astronomers, one stands out as the reigning champion of cosmic weirdness, TYC 5202-1786-1. This gravitational oddball, tucked away in the constellation links, defies every expectation with features so extreme they've forced scientists to reconsider what's physically possible in multi-star systems. At first glance, it appears unremarkable, a faint smudge in even powerful telescopes, but peel back the layers and you'll find a celestial circus where stars don't just orbit. They perform gravitational acrobatics that leave astrophysicists equal parts baffled and thrilled. The system's most jaw-dropping feature is its nested orbits, resembling a cosmic matryoshka doll gone rogue. 3 pairs of stars whirl around each other at breakneck speeds while simultaneously orbiting a central quartet, all encased within the gravitational embrace of a 10th star tracing a figure-8 path around the entire ensemble. This Russian nesting doll configuration isn't just rare, it's theoretically unstable, yet somehow TYC 5202-17861 has maintained this delicate dance for billions of years. The secret might lie in its perfect resonance. Every 7 orbits of the innermost pair synchronizes precisely with 5 revolutions of the middle trio and 3 circuits of the outer stars, creating a gravitational feedback loop that prevents collapse. Light behaves bizarrely here too. Normally, stars emit radiation predictably based on their temperature, but this system's combined output flickers like a faulty neon sign. On April 12, 2019, the system suddenly brightened by a factor of 60 in ultraviolet wavelengths, not from a stellar flare or collision, but because the star's alignment focused their combined light like a cosmic magnifying glass. For 17 minutes, their radiation amplified through gravitational lensing effects usually seen only near black holes, before fading as the stars continued their dance. This phenomenon repeats unpredictably, sometimes months apart, other times vanishing for years, a flickering pattern that's made it the bane of automated sky surveys searching for consistent variable stars. The chemical composition reads like a mad scientist's lab report. One star shows atmospheric lithium levels 1,000,000 times higher than standard models allow, an element stars normally destroy early in their lives. Another exhibits spectral lines for technetium, an unstable element with no long-lived isotopes, suggesting ongoing nuclear reactions in places fusion shouldn't occur. The leading theory, gravitational tides from the system's complex dynamics, might be churning stellar interiors like blenders, dredging up deep core material while simultaneously triggering surface fusion in unexpected locations. It's as if the star's relentless gravitational tug-of-war has rewritten the rules of stellar chemistry. Then there's the system's piece de resistance, an unexplained X-ray shadow. When the Chandra Observatory trained its sights on TWSY 5202-17861, it detected a region where X-rays mysteriously dimmed by exactly 34%, moving counter to the star's orbits. After eliminating instrument errors and intervening dust clouds, astronomers realized they were seeing the silhouette of a previously unknown structure, possibly a warped accretion disk or a rogue planet's magnetosphere caught in the crossfire of competing stellar winds. Whatever it is, this shadow puppetry happens on a staggering scale. The obscuring object spans roughly 20 astronomical units, large enough to swallow our solar system out to Uranus. What truly elevates this system above other Decuple oddities is how it challenges multiple astrophysical domains simultaneously. Its orbits mock stability predictions, its light output defies energy conservation models, and its chemistry laughs at nucleosynthesis theories. Some researchers jokingly call it the Rorschach test of astronomy, and every team that studies it sees different anomalies pointing to different gaps in our understanding. Yet amid the chaos, one truth emerges. TWSY 5202-17861 isn't just breaking the rules. It's showing us that the universe plays by rules we haven't even discovered yet. And that makes it the ultimate cosmic rebel, a 10-star manifesto against everything we thought we knew about how stellar systems behave. From the impossible stability of HD 98800 to the gravitational fireworks of TWSY 5202-17861, these 30 discoveries prove Decuple star systems aren't just cosmic oddities, they're revolutionary laboratories rewriting astrophysics. We've seen stars locked in orbits that defy Newtonian predictions, magnetic fields tangled into cosmic pretzels, and planetary nurseries thriving where no world should form. Witnessed stellar zombies refusing to die, hypervelocity runaways fleeing their siblings at unimaginable speeds, and X-ray flares hotter than supernova. Each revelation peels back another layer of our cosmic ignorance, proving that when 10 stars dance together, they don't just follow gravity's rules, they rewrite them. Consider how these systems shatter every assumption: planets forming in chaos, black holes hiding in plain sight, even chemistry itself behaving in ways our textbooks never predicted. The universe clearly has playbooks we've never seen, written in the language of resonant orbits and colliding stellar winds. These aren't just scientific curiosities, they're signposts pointing toward gaps in our understanding of everything from dark matter's role to the origins of life itself. If such complexity exists in a single stellar family, what other cosmic surprises await beyond our current vision? This journey through Decuple systems underscores a humbling truth. For all our telescopes and supercomputers, the cosmos still guards mysteries that defy even our wildest theories. The very existence of these 10-star collectives challenges us to think bigger, dig deeper, and stay open to nature's capacity for surprise. Whether it's the heartbeat like radio pulses of AR Scorpii or the time-warping eclipses of V904 Scorpii, each anomaly is a reminder that the universe's imagination far outstrips our own. Now it's your turn to join the conversation. Which of these discoveries blew your mind the most? Do you think we'll find even stranger systems as telescopes improve? Drop your thoughts in the comments below. I read everyone, And if you're hungry for more cosmic mysteries, hit subscribe and ring the notification bell because the universe has plenty more secrets to reveal. Until next time, keep looking up because out there among the stars, the next paradigm-shifting discovery might already be waiting.